So last time we talked about Slater determinants. Today we're going to talk about a different principle that is very helpful in computational chemistry that you guys have actually used. We're going to solve one of them by hand so you can see how the process is done and justify how to use this principle. The principle that we're going to talk about today is called the variational principle. The variation, principle. Which is all about getting a wave function of some system. So the direct quote for what it is if an arbitrary wave function is used, so one that we don't really know if it's the exact answer or not, to calculate an energy, the value calculated is never less than the true energy. So basically, if we come up with, we never know the wave function exactly. If we come up with an arbitrary wave function, it has to have, it produces an energy that is greater or equal to, but never less than the actual true value of the energy. Okay, so let's try to justify this. Let's show that that is true. Justification. So the first thing we're going to do is we're going to consider a normalized and orthogonal wave function. So consider a normalized and orthogonal trial wave function. Let's remind ourselves, what does the word normalize mean again?
You integrate squaring it, you'll end up
1 multiplied by its conjugate through an integral equals 1.
Yeah. Yep, everybody had pretty much the right definition. And remember, if we have an unnormalized wave function, what do we introduce in front of the wave function?
Normalizing constant.
Yeah, normalizing constant, and so there's some normalization constant to make this true. Okay, the word orthogonal, what does orthogonal mean?
I mean that you take the integral of phi times some operator, or is it no operator in it?
No operator in this case.
Okay. That if those two things are equal, that should equal 1. If they're not equal, they equal 0.
Yep, if they're not equal to one another, the result is 0. So remember, that's what orthogonal means. That's going to help us out a ton in a little bit. Okay. So what we're going to say is we have a wave function. We'll put psi trial. And it's going to be comprised of a bunch of basis functions. We've got a summation n, C of n, phi of n, where phi is our basis function, c is the contribution that it makes to the wave function. Okay. Now, how would we find an energy? The associated energy is given by E is equal to the integral. We're going to look at the trial wave function, the complex conjugate of it. We just had the regular trial wave function d tau. What are we going to need in the center here to get an energy out?
Some operator.
Yep, some operator, specifically what operator?
Okay, I guess we're just looking for the kinetic energy operator.
Well,
Or we're
nope,
looking for total.
we're looking for total energy. So what do we do for total energy?
Each hat.
Yep, each half. That Hamiltonian operator.
Doctor. Senior sun passer.
Yeah, senior sun passer. Wow, the highest of honors.
Oh, maybe in 2 weeks I'll get there.
Mm,
2 weeks.
Maddie, you're gonna feel so good once it's over. This weight
Yeah.
was lifted.
mm.
And
It
then
does.
2 seconds later, I was laid off.
I just gotta get through this Friday and then redo it next Friday and I'll be good.
Oh,
Woo!
As he says, "Woo."
No, you're gonna do it.
It's like, yeah.
You're gonna get it one and done. I feel confident. So we're gonna call the true wave function. We're gonna call that psi sub 0. So this is the one that gives the actual energy. Gives the true energy. And we're gonna call that true energy E sub 0. Now what we want to do is we want to gauge what's the difference between the energy with our trial wave function and the true energy. So now consider the difference between E and E naught. So we got E minus E naught. We've already come up with an expression on how to find E. What's that going to be?
Just the integral of phi trial
Yep,
times here. Hamiltonian.
Hamiltonian d tau. Now minus E naught. Let's come up with an expression for E naught. In that case, it would be E sub 0, right? However, what we're going to do is we're gonna do something a little bit trickier. We're gonna put E naught here, and we're gonna pretend our trial times this is actually equal to E naught. We could put in that Hamiltonian, but that's going to get us the same result. So we want to look at something a little different. Okay, now we're going to do something a little strange. We can shuffle this anywhere we want it to go, right? Like we could put it in between these two functions. The result is going to be the same either way. So we get that. Now we're going to do something that makes mathematicians mad. You see a way we could simplify this? Or what could we do to make this like one term?
Take out the H hat and E naught.
The mathematicians should be somewhat satiated because what we're going to do is we're going to put them like this. So that way, since this is an operator, operators always act in what direction again?
All right.
Yep, to the right, never to the left. Like that. You might be asking, why? We'll get there, don't worry. Okay, so now we have these wave functions. This looks too easy. Let's make it more complicated than it needs to be. What we're going to do is we're going to sub in our expression that we determined up top. So subbing in that wave function is equal to the summation of a coefficient times that basis function. We're going to put those things in. Okay, so what's this going to look like? So all we're doing is just pushing this into there. So now we get integral summation from n by n. And we're going to apply the complex conjugate to each of these values, or terms, excuse me. N I d tau. Okay, we're going to indicate something here. We're going to put n prime, because these n's don't necessarily have to be equal to one another. Okay, well, we can make this a little bit simpler. What could we pull out of here? Or what are these things again? What's this phi term here?
Contribution.
That, oh, the phi is not the contribution.
Oh, no, I was at the C. The C is the contribution.
Yep, C is
So
the
couldn't you take out
contribution.
C for both?
Yep. So it's that's the contribution sign. So let's pull out the C's for each of them. They're still going to need a summation with them. We're going to have n, n prime, Cn star, Cn prime. And then we got this other junk. E naught, E tau. Okay, we're going to do another trick here. Since if we have integral h bar n prime, we're going to say that's equal to E sub n integral n star by n prime d tau. And one more thing we're going to do. Integral psi n star E naught n d tau. What are we going to do there? We're going to do something similar. Can we pull anything out of this expression?
Could be E naught.
Yeah, we're going to take out that E naught.
So that says psi n1. Is that what that is, or is that psi n prime?
That's n prime.
N prime? Okay.
Yep, it's n prime. Because right now, we don't know if n and n prime are the same thing or not.
I see.
Okay. We're going to justify that in a minute. Okay, so now what we're going to do is we're going to take this stuff, we're going to put it into here, and see what we get out of our original expression. So then what we get? Integral, this thing that we were talking about before, minus E naught m prime d tau. That's going to be equal to this expression, but we can pull E naught and E out, right? So this first part, we're going to have En prime minus E naught is equal to the integral phi n star phi n d tau. And therefore, we can say, after doing some more manipulation, E minus E naught, or we can show that this is also true, n prime, Cn star, Cn prime, En naught, integral n prime d tau. So where did this expression come from? Right along here. Well, basically, we used our previous two expressions and that term up here. Okay? So basically what we're trying to show is that these things are equivalent to one another. All right, let's make our lives a lot easier now. What did we say? If we were thinking about the wave function, what did we say about the wave function? What two properties does it have?
Orthogonal and it's normalized.
Yep, it's orthogonal and it's normalized. And we said the basis functions were orthogonal to one another. So since that's and phi n prime are orthogonal, so we got integral n prime e tau. What's this equal to?
I guess it kind of depends on if they're the same or not.
Okay. If n is equal to n prime, what's the result going to be?
1.
Okay. If n is not equal to n prime,
0.
yep. Then let's go back to our expressions and what cases do we only have to consider?
If it is the same.
Yep. So if n is equal to n prime, then our expression becomes a little bit simpler. Minus E naught. So basically we're taking this expression. What does this last term become? Or what does this expression become if n is equal to n prime? So that one that's highlighted in red. So what part of this term goes away if n is equal to n prime?
Just the entire integral part.
Yeah, that part along here. So now all of this is going to become that. And we just leave off that integral at the end. Okay. And since these contributions, they have to be greater than or equal to 1. En is greater than or equal to 1. And we're going to assume that E minus E prime, or En prime minus E naught is greater than or equal to 1. Then we arrive at this expression. So then E minus E naught is equal to that summation that we had before. Prime, Cn star, Cn prime, En prime minus E naught. All of that is greater than 0. And what we can also do is manipulate this around and show that E must be greater than or equal to E naught. Right? Because we can take this term and shuffle that around. So what we've shown here is that if we have a trial wave function, the energy that we get out, this energy, has to be greater than or equal to the true energy of the system. So if we make a wave function up, what's the best job we can do? Or what's the lowest possible energy we can get?
Just what the energy actually is.
Mm-hmm. So question, what is the lowest energy we can get? The answer to that is E naught, the true energy of the system. However, what do you most likely get? Or what's the more probabilistic answer that we will arrive at?
Anything greater than it.
Just E, I guess, or just some value greater than E naught.
Yeah. But we're trying our best. We want to get to that. But with all the approximations we make, it's most likely not going to happen. Okay. Why do we spend so much time talking about that? We're going to be utilizing that soon when we're talking about molecular systems. So what we're going to start to do now is we're going to shift away from individual atoms. We're going to move into molecules. And to do that, we had to cover this principle to get there. Bless you. What we're going to do now is we're going to start talking about mathematical ways to describe a chemical bond. So the chemical bond.
So did we just kind of assume that those couldn't be less than, or that they are greater than or equal to 0?
So, these sub n's?
Yeah.
Yep, that is an approximation. And if you're thinking about, like, if you think about an atomic system, like let's say, like hydrogen and the contribution these s orbitals have to the total wave function,
It can't be
they have to be
0, or it could be more. But
right.
and then what about the E and the E naught? How do we know that like En can't be greater than E0? Like where thoughts would be like.
Oh, like, so where did that come from?
Mm-hmm.
Basically, if that happens, then this term is equal to 0. And in any other cases, it has to be greater than that value. Or we're like, either we're getting a 0 or we're not getting a 0, basically. Does that make sense? Or not really?
Yeah, but like, I mean, is that just through experiment, or is that like, is there
That's
some...
just from the way we originally set up the problem. And if you look at like this part of the expression right here, and we have this mathematics along this line, we could get rid of, like, we have two possibilities. That this portion and this portion both have to follow like that, what do you call it? It's not inequality, what do you call that? They have to follow this expression. They have to be greater than or excuse me.
Greater than or equal to?
Yeah, greater than or equal to, geez, can't talk today. They have to be greater than or equal to 0.
Okay, and
They're
that's
both-
due to just how we set it up. Okay.
And mathematically, like this side and this side.
Mm-hmm.
It has to be true, or else we just end up getting 0.
Mm-hmm.
Does that make more sense?
Yeah.
And then all we did for this like last little bit is basically like we had this term. Like that's our best case scenario. Then we manipulated this through and got E like that.
Mm-hmm.
Okay, so we're going to use this principle a couple times in the future. And we're going to use this to justify why we can come up with these approximate wave functions. As long as we understand the limitation that whatever we come up with, the best job we can do or the lowest energy we can get is the actual true energy, then we're okay. All right. Let's check out the chemical bond. Let's come up with a mathematical description for this system. So we're going to consider a wave function of a molecule. The wave function of a molecule. So we're going to have, well, we should put wave functions because there's a couple different of them. We're going to have psi sub I. We're going to put a superscript molecule. Now, if we were to come up with the wave function of a molecule, what would it depend on? Like if we could distill everything down to the more basic things that the wave function of the molecule would depend on, what would you need to consider? So R, yeah, when you say R, Maddie, what do you mean?
The radius.
Yeah, a little radius of what specifically? Like what particle?
Alpha particle.
Nope, not alpha particles.
From R1 to R2. Like that kind of radius, you know?
Or are we just going?
Like
Yeah.
our molecule.
Electrons.
Electrons. Yep, Sarah's got it. Electrons. Dropping the mic. Boom. There we go. We're talking about electrons. What else are we talking about?
The nucleus.
Yep, the nuclei. So we're gonna show the electrons coordinates with R, little r, and the nuclei with capital R. Okay, so where R sub n is the position of the electron, and capital R sub n is the position of the nuclei. I will say nucleus n. The electron, and there we go. Okay. What we're going to do now is we're going to use one of the approximations we talked a little bit about in lab. So using the Born-Oppenheimer approximation. So what does the Born-Oppenheimer approximation say? Do you remember? Or do you know what
Oh,
it
it's
had?
about rest mass versus not.
It has to deal with masses. It also has to deal with motion of electrons and the motion of the nuclei.
That, oh, the nuclei motions don't matter.
Right, basically. And why don't the nuclei motions matter?
Because for how much they move, the amount of like change that they're going to cause to energy is so small comparatively to the motion of the electrons.
Yeah, so the
Similar
electrons
to
are,
like kinetic energy of like the two. Like just
Yeah.
kinetic energy of the nucleus is minuscule compared to that of an electron.
and if we're looking in the time scale of the electron, which one moves faster, the nuclei or the electron?
Electron.
Yeah, the electron's moving so much faster than the nuclei that if we could pretty much, in the reference of the electrons, the nuclei look like they're not moving at all. So the electrons move very fast compared to nuclei. How do you spell nuclei? That looks wrong.
I think it's EI.
Yeah, there's an E, L-E-I.
L-E-I. Yeah, sure. Looks better. Okay, so what we can do now, we have our original wave function. What we can do is we can split this up into two wave functions. We have the Born-Oppenheimer approximation, where we can say the electrons move independently of the nuclei. And so on. Okay. So we've split that up. What we're going to do next time is we're going to look at the Hamiltonian of a molecule. And we're going to consider what do those terms mean. I'm going to tell my phone to shut up. And then we're going to try to come up with some approximate solutions. From there, we're hopefully going to be able to describe like what a bond is through something called an overlap integral, and we'll eventually get into Huckel theory. Okay, so that's kind of where we're leading from here on out. Are there any questions about the material that we covered today? We kind of jumped around a little bit in terms of the book. Basically, the point of what today's lecture is if we come up with a wave function, the best we can do is get the true energy or higher energy. Okay. When it comes to more descriptive parts of the chemical bond, we're really gonna get into that, and we're gonna talk about the mathematics behind that. And as you guys can tell, what do you think about the complexity of these wave functions and like solving these systems? Do you think we're going to be able to do that by hand?
You're probably gonna come complex.
Yep, it's really complex. It's never done by hand anymore. It's all done through computers. But this is what all the computers do. They go through, they solve these problems. Okay? All right.